Good afternoon, everyone, and I don't know, maybe good morning still in United States. So today I'm going to talk about concrete under nanoscope and how nanotechnology can change the concrete world. I'll present some of the results of my research of my research group for maybe last 15 years. And today I'll briefly speak about high performance cement and concrete. I'll talk about nanoparticles for concrete application in concrete. I'll speak about use of nanofibers. I will mention about work on mechanochemical activation and production of nano-seeds. I will cover some aspects of fiber reinforced composites. We will discuss superhydrophobic admixtures and also photocatalytic materials. I hope I will have I have sufficient material for 1 hour, but I hope I'll stay within the time frames. And so let's start. And today we all discuss concrete, and most probably you've seen similar slides earlier today. And I just like to briefly mention that really we all deal with concrete because it is such a wonderful material, and it is widely used in civil and transportation infrastructure. Because concrete is such widely used material, the production and use of Portland cement is also considerably high, and we all are dealing with improvement of this material because even small improvement of concrete performance can make a significant impact on environment and significant impact on economics. And question always comes, do we have any issues with concrete? You see it's widely used and it looks like it is a convenient material and material of choice for many applications, but do we have any issues really? Do we know how to use it effectively? And can you do it better? Also, can we produce concrete using green technology? Can we really focus on making it environmentally friendly? And if we look on this chart, very popular in the United States, every year, American Society of Civil Engineers, they do study, and this is, I believe, it was latest. Maybe there is new published recently, but I'm not aware of it. But I'm tracking this for maybe last 10 years at least or more. And really we have in the United States, our infrastructure makes higher than D grade. And again, I don't know if you're familiar with the grades we have in US. D means failing grade. Basically, it means you cannot really graduate from your university with the D grade. You need to take this class again, or you need to go and take entire program again. So very often we feel that more money just simply required. So give us funding and we will do beautiful infrastructure and we can fix all the problems with in construction. And this is the approach Federal Highway Administration is thinking that, well, they can fix it, they can do it if they have more money. Reality is most probably it is not sufficient to have just more funds. More knowledge is required. Some statistics from Wisconsin. So I live and work in Wisconsin, which is on northern, one of the northern, central northern states in the United States and bordering Canada. And most probably it is the coldest and having tough conditions for concrete exposure. And you can see that bridges are like 9% are structurally deficient. We have about 20% of dams structurally deficient. If you look about public roads, 30% in poor condition. So really, really very sad picture. So we do have problem with concrete durability. And if we want to attack concrete durability, we need to understand that concrete is porous material, and so moisture or basically liquids or ions gases can easily pass through the concrete structure if concrete is not designed to resist such type of effects. And obviously, as soon as concrete is wet or subjected to flows of fluids, it can be subjected to freezing and thawing failure, can fail because of alkali aggregate reaction, can fail because of sulfate attack, and chemical attack, which is we often see again here in Wisconsin because of use of de-icing and anti-icing chemicals, and which causes as well physical salt attack and corrosion of metals. And so the durability obviously is a great challenge we have in current state of practice, and obviously something to do with fundamental properties, and better understanding again is required to make a better job on construction sites. Obviously, the effect of water to cement ratio was already discussed earlier today, and we need to understand also effect of curing. So usually what we know about concrete in the lab is definitely material which is perfectly cured in laboratory conditions. What happens in the field, often we don't have adequate curing. And so you can see that curing is very important to formation of proper capillary structure and formation of mesopores rather than micropores, which are easy penetratable by fluids, and which are causing the failure of material under environmental exposures. So basically, if we think about water to cement ratio to be a key parameter, and obviously if you have water to cement ratio less than 0.5, it will result in a better compressive strength, but what is more important, in lower permeability. So lower capillary porosity and lower permeability. And this is our target. Obviously, in the field, curing is a big issue. And I just ran this experiment back in Mexico when we had a construction project next to our university, and I observed that we had certain temperature fluctuation and certain humidity fluctuation. So you can see that rainy days and dry sunny days were changing, and I've seen concrete was actually placed in a very important structure and without proper curing. And I just ran experiment with my students. So we had two types of concrete at 0.45 water to cement ratio, 0.6, and we tested them at different exposure conditions. So for one day, materials were cured at the same the molds in the same conditions, but after one day they were exposed to outdoor exposure, and you can see the profile, and other were cured in the lab and subjected to moist curing. So what we would expect normally from this concrete at moist curing, you can see that if you have a high water to cement ratio, you would have, and difference between these two concrete types would be about 100 kilograms per meter cube. And in order to get your compressive strength, design compressive strength for concrete at 0.6 water to cement ratio, you really need to produce concrete at water to cement ratio 0.5, means use 100 kilograms of cement more in order to compensate for poor job site conditions. Roughly, you can see you lose about 10 megapascal of your compressive strength under such conditions. And this is because of rapid drying and poor microstructure, while you under perfect moist curing conditions, you form a very beneficial microstructure. And if you apply the icing chemicals, if you use salt spray, and you have all these de-icing operations, Obviously, you have under freezing and thawing cycles. You can have, which we have about 50 per year in Wisconsin. You have premature failure of material. And in addition to this, you can see that concrete is subjected to different forms of, especially on the pavements here, different forms of mechanical action. We initiated a research program with Department of Transportation here in Wisconsin, and we suggested to investigate the role of optimal concrete design. And basically, we decided to look further on effects of fly ash and different types of fly ash, Class C and Class F. And Class C is high calcium fly ash, and Class F fly ash, silicon dioxide rich fly ash. And we propose to revisit aggregate packing and aggregate particle size distribution, so we have a better structure. And we proposed also to use modern superplasticizers to improve the performance of concrete. And you can see that if you look for reference concrete, it was considerably improved when we used modern polycarboxylate-based superplasticizer. So again, Department of Transportation is happy with 4,500 psi concrete, and which is roughly 30 megapascal concrete. And but at the same conditions, this can be considerably improved if we just simply use polycarboxylate superplasticizer, or it can be even further improved, considerably improved, with we use combination of polycarboxylate superplasticizer and Class C fly ash. And obviously, strength is not really a big issue. It looks like we know how to handle strength. We know how to improve strength. Important parameter was, of course, the durability. So you can see that all the types of concrete we have, they had considerable air entrainment, and we use entraining admixture, again, modern grade entraining admixture. So sometimes the air content was reaching almost 10%, 9.8%, but some mixtures were as low as 5%, so range of 4%. So the range of air contents, we still had a good, relatively good durability factor, means freezing and thawing resistance was very good, and relatively low mass loss for the concrete under freeze-thaw exposure. Obviously, if we look deeper on different type of fly ash, you can see that strength development can be really boosted with use of polycarboxylate superplasticizer. Obviously, we can see that the Class C fly ash was overperforming Class F fly ash, and even in combinations like 15% combination of Class C and Class F fly ash, we had still relatively good performance, reaching the performance of reference Portland cement concrete. So especially in 1 year, we didn't see the difference between this type of concrete. So again, up to 30% of Class C fly ash and 15% of Class F, or 15% of Class C and Class F can be used again when we combine this, when we use fly ash in combination with polycarboxylate superplasticizer. The benefits of using Class F actually fly ash were with producing concrete with a very low permeability. Most of these concrete types had very low permeability, but still the Class F fly ash based concrete had extremely low permeability. But what we've seen actually that, and this is salt scaling, basically effect of de-icing salts on the surface of concrete and accelerated erosion of concrete due to freezing and thawing. Usually ISTM test constitutes 50 cycles. So if you look for concrete Portland cement 1 and 2, those were really passing tests. concrete with based on Class C fly ash, they pass the test, but concrete with Class F fly ash, any combination, really didn't pass the test on after 50 cycles. So there is really concern. So we have some benefits, but we still have challenge with salt scaling. Well, if we look for concrete challenges, obviously we know how to tune concrete for strengths. We understand the durability at the lab scale. Obviously, we still need to implement it in the industrial scale. Obviously, we have a better idea about sustainable concrete, how to really improve the use of supplementary cementitious materials, and how to reduce Portland cement consumption, and how to reduce energy and carbon dioxide emissions. But can we do better, really? Obviously, the goal for future development is to develop new functionalities and to see new features embedded into concrete, into conventional material. And I'm not going to discuss all the possibilities here today, but I'll touch base on superhydrophobic properties. I'll discuss photocatalytic properties today as well. And today I'll still speak more about nanoparticles and nano-engineered concrete. Obviously, if we look for concrete, we understand that properties and degradation mechanism, they really occur across multiple length scale. And as small as we can now detect is nanoscale, and the properties at macro scale definitely can be manipulated by improvements at nanoscale. For example, calcium silicate hydrate, which is the main building block of concrete hardened cement paste, is a nanomaterial at nanoscale, and this can be detected. So first we had artist renderings for the CSH clusters, and after we were able to see it with atomic force microscopy. And again, when we speak about nanotechnology and nanoscale, we suggested this type of scale. This is now American Concrete Institute approved scale of the sizes, which may be different from classical IUPAC classification or classical capillary voids specification. So basically, it is very simple metric type of description of the pore sizes. And basically, well, not the pore only sizes, but the dimensions related to concrete technology. But basically, whatever is less than 100 nanometers and more than 1 nanometer is at nanoscale. And this is where we really can make a considerable improvement of concrete structure. How this can be achieved? Well, we can investigate concrete structure at nanoscale, and so we can understand it better, and we can improve and fix whatever is wrong at nanoscale. And we can produce nanoparticles and use nanoparticles for improvement of the structure of cement-based materials. We can use nanosized CSH seeds for accelerated hydration, and we can use nano-dispersed cementitious components. We can have nano-reinforcement. We can do modification of surfaces by nanolayers. And what else? Well, we have many other opportunities which we're going to discuss today, including how we can be green with nanotechnology. I think story about nanotechnology, concrete nanotechnology starts with, of course, with instrumentation which we have available now to investigate structure under, for example, transmission electron microscope. And so we can see smaller elements, and we can produce small elements such as silicon dioxide nanoparticles, nanosilica. And obviously, many of us are familiar with silica fume or metakaolin. which were materials enabled us to produce ultra high performance materials. But nanoparticles can be also extremely powerful products, can be used for high performance and self-compacting concrete. And if you look for this relatively old diagram, which we proposed back in 2005, if you look for specific surface area and particle size diagram, we can see that all concrete materials, they kind of follow this straight line. And if you look for conventional concrete, this is what we can do with a conventional set of aggregates, Portland cement, and potentially fly ash. This is what I was discussing at the very beginning of my talk. Obviously, when we have available new components like silica fume and metakaolin, and we were able to achieve high strength, high performance concrete in a relatively easy way. Now, when we have smaller components with higher surface area, with higher reactivity, we can produce nano-engineered concrete. And nano-engineered concrete, it's not only high-strength concrete, it's not only concrete tuned for extreme durability, but it's also concrete with special properties which we can achieve incorporating different nano products. So not necessarily nanosilica here, but any other nanomaterial can be used. And the idea was also that that obviously when we speak about nanoparticle application, we discussed that proper dispersion is extremely important, because if nanostructures are not dispersed, if they are present in form of agglomerates, they're not they are being nanomaterials themselves. They are not really acting as nanomaterials in complex structure of hydrating Portland cement. So we like to have them dispersed. And when we disperse them, usually it may happen in industrial conditions. So on the job site, in the lab, we may receive already perfect dispersions of nanoparticles, and often in the liquid form. And so they look like milky substance, like in this picture, which was given me by Brian Green, who was among the first, together with Mario Calipardi as well, use these products in concrete. And obviously, the addition of nanoparticles was studied to improve the mechanical properties. And there is a pioneering study of Antonio Porra and his group from Bilbao. Obviously, the percentage of nanoparticles here is compared to the conventional silica fume. So you can see silica fume, those are black dots. We know that silica fume is starting to be effective most probably after 8%, and can be used in some applications up to 20%. And when we compare nanosilica, you can see nanosilica is really becoming effective at relatively small dosages, less than 5%, less than 10% for sure. And if we compare effect of nanosilica on compressive strengths of Portland cement systems, we can see that that flexural strength is actually enhancement of flexural strength versus compressive strength was actually was better if we compare the effect. And obviously, my research group was discussing the use of nanosilica at extremely small dosages. Generally, we would use less than 1%, and often we would use less than 0.5% the dosage. And the idea was that nanosilica and nanomaterial should provide considerable improvement at relatively small dosages. Otherwise, it may not be effective economically and practically due to different reasons, so which we're going to discuss now. When we speak about production of nanoparticles, where those are coming from, and there are different methods to produce nanomaterials. I'm not going to cover all, but something what we tried in the lab, we use sol gel method, which is relatively easy method to realize in the lab. And you use precursor, usually TIOs, and use alcohol environment, and you use you can produce it in acidic media, you can produce it in alkali media, and obviously the product you have is nanosilica and alcohol as in solution. And obviously, as soon as you have as a result of this reaction, you have hydrolysis first, and you have polymerization. So you have formed Sol and basically dispersion of nanoparticles in alcohol, and water. And removing of alcohol sometimes is challenging. Sometimes there are elegant solutions. But obviously, the path we usually use is to produce a wet gel, and after evaporate the solvents and produce xerogel, and from xerogel, raspberry structure to produce particles for concrete application. Obviously, you can produce dense ceramics by further sintering, and we, of course, for concrete applications, we would rather use as dispersed products as possible. Obviously, you have another way to produce aerogels, and obviously from aerogels you can produce also very good particles. But again, if you still use the way to remove the alcohol and filter the particles out of the solution, basically dilute and substitute the alcohol with water, you can produce direct dispersion of the Sol from in water with very little quantity of alcohol, and you can further use this as a cement applications with cement-based materials. I think this direction is very interesting, and there are some works in this. But we tried xerogel, and we were trying to produce xerogels which can be easily dispersible. You can see that by changing the conditions of experiment, specifically the water to TiOs ratio or ethanol to TiOs ratio, you can produce particles of different and also vary the acidic media like pH of the reaction, or basic media from 2 to 9. You can create larger particles, or you can create extremely small particles. Based on our results, both pH values were beneficial to produce the particles. Important was to produce those particles at highest dilution rates, so particles were smaller and also easy separatable in the separatable for consequent application in concrete. So if we compare the structure of nanosilica to silica fume, you can see silica fume is known amorphous product, and here we use silica fume with 95% or more, 98% of silicon dioxide. Nanosilica is 99.99, almost like chemical grade silicon dioxide, amorphous silicon dioxide. So basically, you can have this, you don't have crystalline structure, you have a perfect amorphous structure. So they are very difficult to distinguish if you have just simply X-ray diffraction. So X-ray diffraction cannot be used to characterize the products. Obviously, with amorphous materials, we are concerned with particle size, and the composition is pretty known. As I mentioned that dispersion, and it was mentioned before, that dispersion is extremely important. And obviously, the high-speed mixing and rotor starter type of geometry was used to disperse nanomaterials. Sometimes it is not really working extremely well. So the ultrasonic dispersion is something which is commonly used, and dispersion times can really be relatively long. We speak about potentially 2 hours, 3 hours dispersion times. Obviously, it is not that all the material is dispersed continuously at that time, so you need to do some sort of circulation. Cooling is something which you need to pay attention, because higher temperatures may result in agglomeration of the material, nanomaterials. So instead of dispersion, you may reach the agglomeration, initiate some sort of reaction. So you need to be very careful in dispersion as well. In my research group, we are using combination of rotor starter and also ultrasonification together. They work very well for larger batches when we need to produce, let's say, 1 liter of dispersion, and this really worked well for us. If you have time, you can watch a video on YouTube on nanoparticle dispersion. I think I'll move on just to save time. And when we have nanosilica, produced by sol gel method, so you can see xerogel results in this sort of chunks, which are relatively large particles. But if you zoom, of course, you understand those are the agglomerates of nanoparticles. If you just start using ultrasonification, you can see this round angular particles becoming more round. You can see that due to cavitation, the agglomerates are destroyed and smaller particles are relieved. Well, still, it is challenging to disperse the xerogels. And industry now offers very good products which are produced in using relatively cheap methods. So it is relatively easy nowadays to receive the product. So, for example, in the past, SEM binder 8, which was used by Mario Colipardi and Brian Green in the past, are already history, and we have newer products which may have better reactivity and better effect on compressive strengths. So basically, if we compare the two different particles, you can see that smaller particles, they may affect the workability. So you may need to work with superplasticizer to adjust the workability, but usually it can be easily done. And also that if we speak about the using of these nanoparticles, really SEM binder 50 can enhance the compressive strengths, including like early compressive strengths, including 28 days compressive strengths. And yes, 2% is of these nanoparticles works better than 0.5%. And but again, the improvement is really in the early age, basically 1 day, 3 days, 7 days. So this is when you need to boost your compressive strength. So obviously it is the nanosilica is perfect viscosity modifying product, which improves the cohesion of the mix. Obviously it accelerates the hydration, reduces setting time, increases heat flow because it is again accelerator, and improves the compressive strength. So this is the product which we really I would say relatively cheap product comparing to other products, nanomaterials, which can really find here its application in concrete. Let's discuss other products which we tested. Nano aluminum nanofibers, and we use this for ultra high performance concrete, which usually would require compressive strengths of at least 150 MPa. There were different definitions, but something which I have here is something which is adopted by American Concrete Institute. It should have ductile response, which is realized with discontinuous fiber reinforcement. Important parameter pre and post cracking tensile strengths more than 5 megapascal, And obviously, it is considered to have ultimate durability because of this continuous pore structure. So usually, durability of this material is not really a question, but we focus on mechanical performance. And question is 150 megapascal is quite challenging. To produce 150 megapascal is really quite challenging. So we decided to check the opportunity with nanofibers, and you can see that nanoalumina fibers are relatively small in diameter, but they're still very long. Initial fibers, so you can see that diameter can be in the order of 5 to 10 nanometer, and this is transmission electron microscope on the right. And the length, initial length is actually about 50 millimeters as we receive. But because of the dispersion, we can really achieve a good dispersion of these products. They are easy dispersible. And when we incorporate them into the Portland cement systems, we realize we can have considerable enhancement of heat of hydration. And we still observe some delays of heat of hydration. And this is related with the processing technology, because when we use dispersion of nanofibers, some of superplasticizer is damaged due to ultrasonification, and it is causing the delay in hydration. But you can see that heat flow, really peak heat flows are improved. And we explored also a combination of nanoalumina with metakaolin and also with silica fume. Again, relatively small quantities of these materials. And when we look for compressive strength development, again, civil engineers, they really interested in compressive strength. So you can see black as your reference, and the green is with nano alumina fibers. Yes, we had some improvement of early strength, but also we had some improvement of 28-day strength. Again, but when we discussed using the fibers, we realized better matrix, cementitious matrix is required. So using small quantities of silica fume or small quantities of metakaolin, usually about 1%, is extremely useful for proper combination of proper incorporation of nanoalumina fibers. And you can see that all the strengths, early age strength was considerably increased, and the 28-day strength was considerably increased. And metakaolin worked better for early strength, silica fume worked better for longer term strengths. But again, look for this difference of for compressive strength of 90 megapascal was improved by 15 megapascal. This is really considerable improvement. I can say this is really considerable improvement. And normally for ultra high, which can be used for ultra high performance concrete, because normally compressive strength of 145 megapascal can be relatively easily achieved by Portland cement systems, using different Portland cement systems with silica fume. Going over 150, this is kind of the barrier which would require careful selection of superplasticizer, the type of cement. And so this is becoming a challenge, and which we overcome really with just simply addition of nanoalumina fibers, and also, for example, use of metakaolin and silica fume. So in this way, we can easily produce statistically higher strengths of more than 150 megapascal, relatively easy. So you can see that obviously such high strength, ultra high strength cementitious matrices are useful for ultra high performance concrete, and can be easily combined with different types of fibers. Obviously, polyvinyl alkyl fibers are very popular, But if you look for really ductility, high density polyethylene fibers are the best, which you can see from the charts on your stress strain diagrams for 7 days and 28 days. Obviously, steel fibers are working extremely well if we compare them with polyvinyl alcohol fibers, but obviously high density polyethylene is something which is really helps us to improve the response of this material and produce outstanding product. Well, let's discuss briefly the production of nanomaterials again. So we covered nanosilica, we discussed about nanoalumina fibers, and we discussed briefly salt gel method. And really, can we do a better processing of the and produce nanomaterials from available products in easier way? Basically, can we use a top-down approach in order to manufacture nanomaterials? Can we use mechano-chemical activation, induce dissolution of the minerals which we have available for Portland cement? And obviously, these products can be used for self-consolidating concrete, and obviously we can have relatively non-expensive final product. So how we can do it? Again, this was concept I proposed long time ago, but I'm really close now, only now to realize it. Basically, the concept when I would have a Portland cement component ultra finely dispersed in the system and combined with mineral additives, and so the resulting product would have very little Portland cement in its structure, but all the properties would be at the levels we would expect for a classical Portland cement systems. And this is possible with CSH seed. So if you have a CSH seed incorporated in, obviously you can have a better structure than you would have just with solar nanoparticles. And you can understand because nanoparticles are participating in the reaction, but CSH seeds are really the products which can have a better acceleration and better structure filling properties, and can act also as what I call super glue, and even like work with less reactive particles of supplementary cementitious materials. To prove this, we run an experiment to produce a nanoseed, CSH nanoseed or hydrated cement products using experimental program. And again, if someone is interested, you can have a look on this paper published back in 2015. And activation time, we use different activation times. We use different cement replacement with activated cement slurries. You can see that most of the compositions were extremely fluid. And we used also super plasticizer to produce the activated material. If we realize activation and due to mechano-chemical activation, so you can see that degree of hydration is considerably increasing, and after 60 minutes you can have considerable volumes of products of hydration. So you can see Portlandite, you can see ettringite appearing, you can see main peaks of C3S, C2S are really reduced after 60 minutes. So obviously Portland cement can be used as a precursor for nanoseed production. And if you look for mechanical performance, so again, we had different quantities of activated product, and we had the different activation times. We just realized that even small activation time and a relatively relatively small quantity of supplementary cement substitution with activated cement really results in considerable improvement of compressive strength. So basically, you can see a reference material of the same composition, and I'm just referring for 28 days, but the same improvement, you can see considerable improvement can be reached in 1 day as well. The improvement for the same exactly composition, but again, some portion of this cement was processed for production of nanomaterial, nano-seed material. We have considerable improvement of compressive strength. This is big deal because again, we use silica fume. We don't use silica fume here. We use super plasticizer, and we use very small quantity of nanosilica for activation, just as a process in viscosity modifying admixture. So this is considerable improvement which we can use for production of self-consolidating concrete. Can we do better? Can we produce green self-consolidating concrete and try to use class of fly ash as a precursor? Obviously, wet milling of fly ash nanoparticle blends with super plasticizer can be realized. And we run preliminary experiment with inert plus F fly ash for 3 hours. And you can see that you can really have effective wet milling and strength improvement with class F fly ash as well. But the major improvements were expected with class C, which is suitable for the as a precursor and formation of beneficial structures during mechanochemical activation. Again, we tried 20% of activated material, same as Portland cement, and we activated it for optimal time for 3 hours. And all the materials were processed and produced. Mortars were produced at water to cement ratio at 0.3. And upon activation, what we realized that we have formation of, even after 3 hours, activated cement. After 3 hours, we have the formation of calcium aluma silicates in such as catoite products after 3-hour hydration. So this is can be easily detected, and those products were actually main acting products of nanomaterials accelerating the hydration process of the system with activated class C fly ash. So if you look for system with class C, we can see some reduction of the heat flow, and as soon as we would use the activated material, you can see that the acceleration is happening. The peak here is flow is higher, and we can see the rapid hydration is happening. Obviously, if we look for class C replacement of Portland cement, there is some reduction of compressive strength, not to 20%, but still not to the level of pure Portland cement. As soon as we say activated system, and specifically activated system with nanosilica, was demonstrating a better strength than Portland cement. And again, process of mechanochemical activation of fly ash is not complex. It's relatively easy to realize, and it has this potential benefits of converting class C fly ash into a material which is improving strength development of Portland cement systems. And yes, this all tests were done at the same water to cement ratio, so we don't have any effect of water to cement ratio. Systems with nano seeds where they were extremely fluid, and you can potentially have further strength improvement by control of water to cement ratio, but it was not the aim of the study. It was important for us to demonstrate that these products can really enhance the performance, and keeping water to cement ratio constant was the important parameter to keep. And if you look for activated class F material, obviously activation and versus reference class F really improved the response, but not first day response, but 7 and 28 days response was really very similar to that of Portland cement, reference Portland cement. So class F material didn't form any nanostructures, so it was just again 3 hours of milling, and it was still useful, but not really at this early stages of hydration. Obviously, application of this material in self-consolidating concrete was beneficial. So we run an experimental program with two series with 400 kilograms per meter cube and 500 kilograms per meter cube of cementitious materials. And we had excellent flow properties. We had measured that, and this is the range for slump flow, and we had excellent response. So you can see that actually this was low the test of self-consolidating concrete, and we tested also for J-ring test, and we found perfect relationship there. Obviously, if we look for compressive strength development, and again in this experiment we just use class C fly ash. If we would use 30% of fly ash as a replacement, or we have activated material, obviously the 7-day, 28 days strengths, 3-day strengths were really improved in these systems. So it shows the benefits. I have maybe 10 minutes left, and I'll try to briefly cover other aspects of nanotechnology in concrete, which we are really developing. And one is related to superhydrophobicity and enhancement of durability. Obviously, if we want to have a better, improve the durability, if we want to have a better concrete, we need to find ways to control of water ingress. And normally, sealing the surface is not really a good option. So making surface hydrophobic was really working well. And 3-volume hydrophobization, this is something which is ideal to achieve. So how to do it, let's discuss this. And obviously, nature can help us to understand the surface phenomena, and nature can help us engineer and design superhydrophobic surfaces. Basically, if we analyze the lotus leaf effect, we can see that lotus leaf effect is realized by forming the spikes on the surface, and the spikes of the size of 50 to 100 actually nanometers, but some spikes.
Konstantin.
Yes.
Sorry, because we are going long. So how long is your presentation? More?
I said 10 minutes, 7 minutes now left.
Oh, other 7 minutes? Okay.
Yeah, I was planning for 1 hour.
Okay. Sorry.
Okay. Yeah, I'll be done quickly now. So it's there are like a couple of slides. So again, if we can mimic the structure, we can of lotus leaf, we can produce the superhydrophobic structures. And we had classical concrete is hydrophilic. It's absorbing water, but it also has a very low contact angle. So water is easy spread on the surface. And the classical hydrophobic surface is more than 90 degrees. And usually it is impossible to improve it just by surface modification by hydrophobic agent. So superhydrophobic surface is contact angle 150 and very low roll-off angle. And this is what usually we can observe on lotus leaf. And we offered a new definition like over hydrophobic surface between 120 and 150 degrees. And this is what is easy realizable in concrete. And 3D volume hydrophobization can be also realized with proposed idea. Basically, we incorporate the polyethyl hydrogen silane agents, which can provide chemical bond with any silicon structure or silica aluminate structures. And also we incorporate nanoparticles or nanostructures into the surface. And you can see that those can be designed to have a sort of particle deposition, so we can control the roughness there. And with roughness, we can control the surface, so you can see how structure is designed with particles. And so with we can design some reason I don't think it's running, but it's running. So we have a test for contact angle, and you can see droplet is jumping off the surface and it rolls off. So rolling off angle is very close to 0. So we can engineer this type of surfaces. When we apply them on concrete, you can see that wet concrete around this treated patch, and treated patch remains dry all the time. But concrete, surrounding concrete is wet, so it is really subjected to failure. And again, when we test this concrete for freezing and thawing, like we did 400 cycles at -50 C, which is extremely low testing and extremely high terms of testing temperatures. So we demonstrated that this can be performance can be considerably improved in terms of freeze thaw and salt scaling. Well, I like briefly to touch based on photocatalytic materials. I need another maybe 2 minutes. And this is another work which we've done in Milwaukee. This is our experimental setup. So we have a chamber with circulating air. So we supply NOx gas into the chamber, and we have UV lamp which is imitating our sun radiation, and we can check the conversion of NO into depending on concentration, and also calculate abutment, NO abutment for specific conditions. And you can see that some of the coatings are very effective if we use relatively 1.5 ppm is actually something which is concentration of NOx is of interest. And you can see you can have better than 95% conversion of NOx gas in the chamber. So you can see initial concentration. Here we have the UV light started, concentration rapidly drops, converted. Here we switch off the chamber, and chamber is filled with NOx gas, and so the concentration is restored. The compositions are very effective at 15 ppm as well, extremely high concentration, which is more like industrial gas, and can be used for other depolluting applications. This is example which similar coating was applied in Arizona. After a number of years, it was still performing well. And a project we had involved photocatalytic concrete and pervious concrete as a combination. And some example of photocatalytic and superhydrophobic coatings, which can be easily combined together. So you can see ceramic tile coated. This would be wet. It's dry, remains dry, and you can see these droplets there. So again, I have maybe a few seconds to show the nanotechnology of concrete webpage at American Concrete Institute. We always look for new members, student members especially. So if you're not, try to join. We have maybe a first comprehensive report on nanotechnology, nanomaterials, produced by the committee. And this is the front page. We're working on new documents, and ASTM is working on new standard on colloidal silica. So we have a lot of work to do together with my research group. In the past, this is me. If you didn't see my picture well from the presentation. So if you have any questions,